Okay, my calculus people. Here are some related rate problems with cones. So almost always the cone is vertex down if it's water filling up. Sometimes if you have a conveyor belt with sand falling off it, that's a cone with a vertex up. That one's pretty standard. But here we are filling this cone with water, or potentially water is leaking out of the cone, so we're losing. In either case, water represents the volume. Okay, so these are almost always volume problems, and they all should always give you the formula volume equals 1/3 pi r squared h. Okay, which is a problem because we have two variables in here, right? And it's a product rule to take the derivative implicitly, but they don't give you all the information. Usually they only tell you the rate of change of the height or the depth of the water. They don't tell you about the rate of change of the radius. Okay, and they don't have to. Okay, and they won't ever. They're only going to tell you one rate. Because what they want you to understand is no matter what the height of your water is, the radius is a proportion. Okay, so no matter how deep the water is, the radius will be proportionally as wide as it always is. So that's where we start, is by creating a proportion using your maximum values from your problem. Okay, so we start with an r over h equals whatever those numbers happen to be. Okay, the actual radius from your problem of your cone and the actual height of your cone. Because we want to do one thing, and that is write the equation with just one variable. Okay, we don't get a whole lot of practice with this. So that's going to be the first difficult part. Okay, the calculus is pretty easy. The geometry and the algebra is not. Okay, so let's look at an example. Water is filling a conical tank with a vertex down at a rate of 10 pi cubic feet per minute. So water is your volume. So anytime we have water changing, that's the derivative of, that's the rate of change of the volume. Okay, so that's your dV dt. The radius of the cone is 10 and the height of the cone is 20. This is what we use to find your ratio. Okay, that's the only time that we use those two values is in your ratio. So the radius to the height ratio, right? Comparison. So the maximum radius is 10 and the maximum height is 20. Okay, we're going to need this here in a second. Because it says, at what rate is the height of the water changing when the height is 12 feet? We don't know anything about the rate of change of your radius. So when we take the derivative of this formula with respect to time, we're going to have a dr dt in here. Because every variable gets a derivative with respect to time. We don't know anything about dr dt, nor can we find anything about dr dt. So we're going to try and first get rid of our radius and just have an equation with h. And that's the hard part. Okay, so we want to replace r with its proportion in h, which is where this comes in. Okay, let's solve that equation for r. So to solve this ratio that we created for r, and by the way, you have to do this all by yourself. Nobody's going to tell you to do this. You have to know that in these type of problems, we have to do this equation simplification or equation manipulation. So if the radius is 10h over 2, what does that reduce to? That's just h over 2. So the radius is always going to be half the height. Okay, that's the ratio. So as the height is 10, the radius is 5. When the height is 18, the radius is 9. So we're going to take this h over 2, and I'm going to put it right here in my formula. Right? Nobody's going to tell you to do this. It doesn't say to do this in your problem at all. But we have to do it because we only know information about the height. We don't know any information about the radius. So I'm replacing radius with half of the height, right? That is its true proportion. The radius for this problem is always half of the height. So now let's simplify all this down. What is h over 2 squared? H squared over 4. We square the numerator, we square the denominator. So in my numerator I have pi, and h squared times h is h cubed. So I have pi h cubed in my numerator. And then the denominator, I have a 3 times 4, which is 12. So this is my volume formula with respect to height. Right? Only one, or actually two variables, v and h. Okay? So that is hard part number 1. Actually, that is the hard part. Everything after this is pretty straightforward. So now that I know my volume equation, let's come up here and take the derivative. So the derivative of volume with respect to time, that is our dv dt. Beautiful. Now, what is my constant on the right side of my equation? Pi over 12. So pi over 12 is my constant, just like the 1 over 25 was in our other video. Pi over 12 is my constant, so it stays. And now we're going to take the derivative of h cubed. What's the derivative of h cubed? 3h squared times dh dt. Excellent job. 3h squared times dh dt. Now, if you want to right here, we can simplify. The 3 in front of my h squared can reduce with the 12, but it's not necessary. Okay, but oftentimes we can do that, and we will eventually. So let's plug in what we know. We know that the dv dt is 10, right? 10 pi. 10 pi is my dv dt. What is my height? What is the height? When the height of the water is, what's it say? No. At what rate is the height of the water changing when the height is 12 feet? Right? We want our moment in time. When the height is 12 feet, what is our water depth changing at? Okay, so the height that we're looking for is 12. Right? Not our maximum height of 20, but the current height of 12. Okay, so let's do some, I have a 12 in my denominator, and I have 12 times 12 in my numerator. So I'm going to divide this 12 with one of those 12s, right? 144, which is 12 squared, divided by 12 is just 12. I just don't like to do things like, anyway, 10 pi over here equals 3 times 12 is 36 pi dh dt. So my last step is to divide by 36 pi. And 10 pi over 36 pi reduces to 5 over 18. And my units are feet per minute, right? Height is a linear unit, so not square units, not cube units, but rather feet per minute. 5 over 18. Okay, let's see if we can do another. Water is draining from a conical tank, causing the depth of the water to decrease at a rate of 2 feet per hour. Okay, so that means we're talking about the height. dh dt equals -2 because it's decreasing. Okay, causing the depth of the water, which is also known as the height, to decrease at a rate of 2 feet per hour. So our dHdt is negative. Okay, this next information is just for your ratio, your proportion. The radius of the tank is 8 when the height of the tank is 12. So R over H equals 8 over 12. That's where these two pieces of information go. They do not go into our formula. Okay, they go into your ratio. Okay, so volume equals 1/3 pi R squared H, right? Once again, we want to replace R with the ratio from over here. That's why we do it, so we can replace R in our equation and just have H. So the step is the same, multiply both sides by H. And what does 8 over 12 reduce to? 2/3, so 2H over 3. This is what's going to go in here. Okay, we use our proportion in order to find how big that radius comparison is. So now let's simplify this volume formula down. Okay, 2H over 3 times 2H over 3 is 4H squared over 9. Okay, so that one becomes a 4H squared over 9, and I'm still multiplying it by H. So let's multiply all of my numerators. I have 1 pi 4H squared in H. That becomes 4 pi H to the 3rd power. And when I multiply my denominators, H, or 3 times 9 is 27. So this is my equation that I'm going to be taking the derivative of. The volume in terms of H. Only one variable to derive, which is much easier than doing two variables. So let's do that. Let's take the derivative of 4 pi H cubed over 27. Okay, so we start with dV dt, the rate of change of our volume with respect to time, equals, what are my constants? 4 pi over 27. Those are all of my constants. 4 pi over 27. Now, what's the derivative of H cubed? 3H squared times dH dt. Okay? I mean, if there is a good thing, it's that these problems are all done pretty much the exact same way. You're always going to have an H cubed. You're always going to have a constant. So we have 4 pi over 27 times 3. What is the height at this specific moment in time? At what rate is the volume of water changing when the water is 4 feet deep? We're asked for what's going on when the water is 4 feet deep. So that is the height that we are plugging in. And our rate of change was -2. We are losing water at a rate of 2 feet per hour. Okay, so a bunch of multiplication. 4 pi times 3, 4 squared is 16 times -2, all divided by 27. Okay, if this were an FRQ, you could stop right there. AP does not need you to multiply all of that stuff out. Okay, but I do, so let's do it. Calculator says, so my volume is changing at a rate of 128 over 9 cubic feet per hour. And it's negative because the water is flowing out, so decreasing. Okay, these are some tricky problems. but they're all done the same way, one step at a time. Go forth, be good.